Okay, this screencast will be a little quicker than the last one, a little shorter. I just want to go back to worksheet 2 and make sure people understand the path of a charged particle in the presence of a magnetic field now that we've derived an expression for the force on a charged particle as it moves through a magnetic field. So that equation, again, the magnetic force on a charged particle was QVB times sine of that angle. Okay, so this is from worksheet 2, this example right here, and it shows a positive charge entering a magnetic field that's into the page. The velocity vectors in this direction. A couple people struggled with this a little bit as far as the answer, whether it would accelerate or not. Most people got the path right. If you use the right-hand rule, your index finger points to the right, the B field is into the page. So as it gets to this point, since the force on the charged particle has to be perpendicular to its velocity, that's the part of the right-hand rule, it's going to be straight up. So that's going to cause this thing to deflect, and now it's going to be somewhere up here. Well, if you think about it, now the velocity is, again, tangent to the path, but because your finger now is pointing up to the right, and the B field is still in the page, now the magnetic force is off at an angle. Oops. Like this, still 90 degrees. So this is a recipe for circular motion, as you can see. So every time this thing turns a little bit, the magnetic force is always going to be at exactly 90 degrees to the path, to the velocity. And so that's the definition of circular motion. Because that magnetic force is perpendicular to the velocity at all points to the path, there's no work being done. Because remember, work, in order to add energy to the system, the force and the displacement have to be, there has to be at least a component parallel to the force. So if no work is done, no energy is added to the system. So there's no increase in kinetic energy, there's no increase in speed. So it's constant speed. Doesn't mean it's not accelerating because the direction is changing every instant. So that's circular motion. Okay. So I think that should answer a couple questions about that one. This one right here, a couple people got this one wrong also on the worksheet. We've got negative charges, so those are electrons. We're trying to find the direction of the B field, so it's asking us which way should the B field point for this electron to basically be deflected downward. So we know it's got a force downward. So this is one where you don't know the B field, but you know the force. So if I put my thumb downward and I've got my right hand pointing to, my index finger pointing to the right, my middle finger is coming out of the page, that would be for a positive charge. Because this is a negative charge, the B field must be into the page. So I've got a B field that looks like this. Shoot, sorry about that. B field that looks like this all over the place. And you need to represent a B field with more than just one circle. So you'd put a few, make it look evenly spaced, not like I did. So it looks like it's a constant B field. Here the electron's path is out of the paper. Because it's an electron, since it's being bent out of the paper, that means your thumb should be pointed out of the paper, and it's an electron, so the B field, if it was a proton, would be pointed up, so the B field for the electron is pointed down. Again, more than one arrow, because it's a constant B field. So hopefully that answers a couple questions on that. Here's a unique situation for the path of a charged particle when it's not perfectly perpendicular to the B field. In other words, there's an angle theta that's not 90 degrees. Here's a charged particle that's got a component of its velocity that is perpendicular. That's this one right here, but it's also got a component that's parallel. So I'm going to call this V parallel, and this is V perpendicular. Well, as you can tell, if you look at it from the end view, so if I look at it from this way, so if you were checking that out, it would have a circular motion in that plane, but it's still got a component of velocity that's parallel to the B field that's unaffected by the B field. So it still continues to move left to right in this view right here, but because of this component of perpendicular velocity, it's also going to have a circular motion in that plane. So it turns out that's like a corkscrew or a helical path. So it continues to move this way while moving in a circle because of the perpendicular component of velocity. So when you've got a situation where there's only a component of the velocity perpendicular to the B field, you're going to have that helical motion. All right, last thing. We're going to talk about an example that's important, similar to the velocity selector, but this is a mass spectrometer. Very interesting application of this was in World War II when we were building the atomic bomb. They used a mass spectrometer to separate the isotopes of uranium. The naturally occurring isotope is U-235, U-237, I think it is, and we wanted U-235 as the bomb grade uranium. And it's only 1 or 2% of naturally occurring uranium is in the isotope that is bomb grade. So they had to separate the different atoms by mass. And the way they did that is they used a mass spectrometer. So it takes advantage of the fact that a charged particle is deflected by a magnetic field, and they sized the magnetic field so that it would bend the charged uranium. They basically made the uranium an ion by stripping out some electrons and passed it through this field here. So let me just kind of set this up for you. So I'm not going to set up the part that is the velocity selector because we've already seen that in the other screencast. But the interesting part is what happens after the particles leave the velocity selector. They're in a magnetic field. So what that looks like is this is the velocity selector part right here. The particles that are going just the speed you want pass through, and of course you have a B field in that region as well, but out here there's only a B field. There's no E field. So when the particle gets to this point right here, let's say it's a positively charged particle. Actually, it would have to be a negatively charged particle. It's going to be deflected downward. Okay, and if it's in the region of a B field, it's going to be deflected, if this is all a B field right here, it's going to be circular motion. So you're going to have a radius of curvature caused by the fact that this, as soon as it gets into this area where there's no E field and only a B field, that force on the negative charge will constantly be perpendicular to its velocity at any instant. Well, if you remember your circular motion, that's the formula for circular motion. So it turns out that the radius is going to be dependent on the mass of the particle because they're inversely related. So the B field force is the same because the charges on all the particles are the same, but the isotopes have different masses because they have different numbers of neutrons. So you've got the heavier ones are going to have less of a tight radius. They're going to be out here. The lighter ones are going to have a tighter radius because the same force will accelerate them more. So you get the lighter ones will land here, the heavier ones will land here, and that's how they're able to separate the different isotopes by collecting the particles that hit at different locations on a collecting screen there. So that's how a mass spectrometer works. Understand how to do that problem on the last page. You can go back and check it out. We may do it in class, we may not, but it's something you want to know how to do. Okay?